Alright guys, in this lesson we are going to move from graphing quadratics in standard form to those given in vertex form, and you're going to find out that vertex form is fantastic. So as we work through this lesson, I want you to be thinking about why does an a value of 2 make the graph have vertical stretch? So we've talked about that, but I want you to be thinking about why. By the end of this lesson, you should be able to do these 3 things. Given a bunch of transformations, write the equation, talk about the vertex given an equation in vertex form, and then describe all of the transformations that are happening to this equation. Alright, so let's do a little bit of review of the parent graph. So the parent graph of quadratic we learned right at the beginning of school is y equals x squared. So I'm taking any input, multiplying it by itself to get the output. So let's make the table and the graph. Go ahead and pause the video just for a quick review. So hopefully you came up with the parent graph, and the table that we like to use is input 1, input 2, input 3, and see what our output is, and then we know based on that axis of symmetry that those points just reflect across the across the x equals 0 axis of symmetry line here. So what about when we take the quadratic parent graph, y equals x squared, and we give it a coefficient of 3. So what I'd like you to do is pause the video and make a table using those 1, 2, and 3 input values and see what happens to your output. Alright, so hopefully you were able to calculate in the table that I'm essentially plugging in my input value, squaring it, and then I'm multiplying that value by 3. So instead of going over 1, up 1, I'm actually going over 1 and up 3 because I'm taking that squared value and multiplying it by 3. So my normal movement of over 1, up 1 becomes over 1, up 3, which then is that point. So then when I go over 2, normally I would go up 4 because 2 squared is 4, but I still have to multiply it by that 3, so 4 times 3 becomes 12. So that factor of 3 in front of that x squared is going to make my quadratic increase at a faster rate because I'm taking the parent graph and multiplying each point by 3. So you can see that the green is being stretched taller than the black, the parent graph, because instead of 1, I'm going 3 times that. So 3, and instead of going 4, I'm going 3 times that to 12. Alright, what about when the coefficient is half? So go ahead and pause the video and go through that same process and see what that graph looks like. So hopefully your graph looks a little bit wider than the parent graph because now I'm taking the parent graph of squaring the input value and I'm taking half of that out as the output. So this coefficient of 1/2 is going to take the normal parent graph output and take half of it. So 1 squared is 1, half of 1 is 1/2. 2 squared is 4, but I'm taking half of it, so it becomes 2. 3 squared is 9, and half of that is 4.5. So instead of our normal over 1, up 1, I'm going over 1, up 1/2. Over 2, up 4, I'm going up 2 over 2 because I'm going half of what it would be. So the black is my parent graph, and the blue I can see has been compressed or squished down. I'm taking each point and I'm dividing it in half, 9 to 4.5, 4 to 2, 1 to 1/2. And then the reflection is happening over here. So that coefficient is really impacting the output depending on am I increasing by a number larger than 1 or am I taking a fraction of what it would be. Alright, so for this one you're going to do a little bit of exploring. So if you notice, we have the parent graph right here. And what I want you to do is I want you to type into your calculator in your graphing. I want you to do x squared, go to the y equals, go to x squared minus 4. And then I want you to graph it. So zoom 6 will put you in a standard screen if your calculator is still in the zoom 9 mode. And I just want you to describe what happens to the parent graph. So we know what the parent graph looks like on the calculator. So take your calculator and observe and just jot down any notes that you notice of the graph. How does it move? And then once you've done these 4, I want you to come up with a rule when I'm adding or subtracting to the end of the function, what happens to the parent graph? All right, so hopefully you're able to see that when I add or subtract onto the end of just the parent graph, it shifts the graph up or down. So when adding or subtracting on the end, we're shifting up or down. All right, so we're going to go through that exact same process. So go ahead and use your calculator to take the parent graph and see what happens when I add or subtract inside of the parentheses. So hopefully as you explored with your calculator, you saw that adding or subtracting inside the parentheses took the parent graph and moved it right or left. And it did the opposite of what I would normally think. I would think if I'm subtracting 4 up here, then I would move left 4, but it actually moves it right 4. And we're going to talk about why that happens. But I just said it shifts left or right, opposite of what you think, just as a reminder. Because when I added or subtracted on the end, it did exactly what I thought it would do. Up for adding and down for subtracting. All right, we've already explored a little bit with the coefficient in front of the parent graph x squared term. But what I'd like you to do is still go through this process and look at these different graphs. And now that you have a little background knowledge, do predicting before you graph it. All right, so you hopefully saw that when the fraction was in front of the coefficient, so when we were multiplying by a number between 0 and 1, so the negative has nothing to do with it. The negative reflects it over the x-axis. So it's not about numbers smaller than 1, it's about numbers between 0 and 1, so fractions. And so that's where it got fatter, and then numbers larger than 1 made it skinnier or taller. And we talked about vertical stretch and compress already, but I just wanted to use those general terms in this exploration. All right, so let's get into vertex form, because knowing vertex form will make your life so much easier. So the A that is in front of the vertex form, this is going to be the same as what the A does in standard form. So that's kind of nice. It determines two things. It determines reflection. So if A is negative, obviously I'm reflecting over the x-axis. And then it also determines whether it's stretch and compress. So if A is larger than 1, then it's going to be vertical stretch by whatever that factor is. So if it's 3, then I'm multiplying everything by 3. And if A is between 0 and 1, then it's going to be vertical compress by whatever that factor is. So the A, it's kind of nice that the A in standard form and the A in vertex form do the same thing. All right, let's talk about the H. All right, so if you notice, the general form for vertex form is y equals A times the quantity of x minus h. So the general form says take x and subtract whatever h is. So if h is positive, okay, so positive is a movement right, then it will look like x minus h. But if h were negative, so if I had a left movement of 3, so that would be minus 3, and I put minus 3 in here, minus a negative becomes a positive. So that's why inside those parentheses it does the opposite, because the general formula is x minus whatever the movement is. And so if it's positive, then it will say x minus that movement, and if it's negative, it will become x plus that movement, or x plus that value. So this is the h determines the horizontal shift. So if I'm adding, I shift to the left, and if I'm subtracting, I shift to the right. So if this sign is plus, I shift to the left. If this sign is subtract, I shift to the right. Now the cool thing is this is very similar to when you talked about absolute value shifts when we were in Algebra 1. All of these things follow the same general rule. If I'm inside the parentheses or the absolute value or whatever, that's the left-right movement. And if I'm outside, that's my vertical shift or my up-down movement. So K is the number that is the value that determines the vertical shift. And this follows our natural intuition because the formula is y equals A times the quantity of x minus h squared plus k. So here it was minus the shift value. Here it's plus the shift value. So plus 4 being a positive movement, still stays positive plus. But if I had a negative movement of 4, I'd put a minus in, and a positive times a negative still becomes minus here. So this sign is really the reason that it does what our intuition thinks or what we don't think. So adding shifts it up and subtracting shifts it down. So this formula right here, this general format, is something you want to memorize. It's very important that you know what these different A, H, and K values do, and to be able to write, you're going to have to be able to write this formula given different transformations. So y equals A times the quantity of x minus h squared plus k. All right, so vertex form can be a little confusing at first until you catch on to it. Once you get the hang of it, it becomes the easiest thing to do. So here are some guiding questions that help me think through this process of graphing from vertex form. First of all, I ask myself, okay, what transformations have occurred to the parent graph y equals x squared? So where are there numbers showing up other than y equals an x squared? And then I think about, okay, with those numbers, what type of a shift? Is it a stretch, compress, a shift, or a reflect? Does each of those transformations mean? Then I ask myself, okay, now that I've identified what shifts have happened or what reflections or what stretches, where is the vertex? So my shifts will always tell me the vertex because the vertex is going to either shift left, right, up, or down. So those H and K values are what's going to tell me where my vertex is. And once I graph the vertex, if there's a vertical compression or stretch, then I need to apply that to the parent graph table. So that 1, 1, 2, 4, 3, 9 table that we use. So this right here is going to help me think through this process. All right, so my first question is always, what transformations have occurred to the parent graph of y equals x squared? So I'm going to come over here to this first one, and I'm going to see that this transformation of minus 3 and plus 4 have occurred. There's no a value in front of it, but I do see the minus 3 and the plus 4 have modified the parent graph of y equals x squared. So then I'm going to ask myself, what type of shift, reflection, stretch, or compression does each transformation, so each number that I highlighted, what does that have? So I know that when I'm adding or subtracting on the outside of the parentheses, this is a vertical shift, and it's positive, so it's going up 4. And then x minus 3. So the formula is x minus that value that it's moving, and since it's 3, then it's going to move right 3. I don't have any vertical compression or stretch, and I don't have any reflection. So I've identified each piece of the transformation. So the next question is, where is the vertex? So the vertex of the parent graph is at 0, 0. It always starts at 0, 0, the origin. So if my graph is shifting right 3 and up 4, every point is moving right 3, up 4. Well, if the vertex is at 0, 0 and I shift it right 3, that means the x is changing by 3. And every point is going up 4, then 0, 0 will become 3, 4 as my vertex. So then my final question is asking about vertical stretch or compress. So it's taking that table of 1, 1, 2, 4, 3, 9 and asking if it's going to change in any way. Well, since there is no a value, or a is 1 essentially, then I'm doing everything to the same ratio. I'm multiplying every output by 1, which will keep it the same. So this one is going to keep that same parent graph table of 1, 1, 2, 4, 3, 9. All right, so what I'd like you to do is pause the video, and I want you just to identify in example 2, just identify the transformation. So answer that first question of what transformations have occurred to the parent graph of y equals x squared. All right, so hopefully you were able to identify that it has an a value of 2. It has an h value of actually negative 3, because remember the formula is x minus that value, and so the only way to get a plus sign when I'm subtracting is to bring in a negative number. So it actually has an h value of negative 3, and then it has a k value of positive 1. All right, so go ahead and pause the video and see if you can come up with what transformations will each of those values have on the parent graph. All right, so hopefully you were able to identify that the 2 out front is going to give it a vertical stretch of 2 The plus 3 on the inside is going to shift the graph left 3, and then the plus 1 is going to move the graph up 1. So where is my vertex? Go ahead and pause the video and see if you can determine the vertex. So think about if I'm starting at 0, 0, and I go left 3, up 1, what ordered pair is that going to be? All right, hopefully you were able to determine that if I go left 3, that's a negative value of x, and up 1 is a positive value of y, so my vertex is going to be at negative 3, 1. And then our last question is about that parent graph table. So because there is an a value, that parent graph table is no longer going to just be 1, 1, 2, 4, 3, 9. How is it affected? Well, I'm taking each value that should be the output and I'm multiplying it by 2. So normally I would input 1 and I would get 1 out, but now I'm multiplying it by 2, so I'm actually going to get 2 out. So it's going to be an up movement of 2. When I input 2, 2 squared is 4, so normally I would get 4 out, but I'm multiplying it by 2, so I'm actually going to go up 8. And then when I do 3, 3 squared is 9, but I'm multiplying it by 2, so that actually gives me 18. So my right-left movement of 1, 2, and 3 now have an up-down movement of 2, 8, and 18 because it has that stretch by a factor of 2. So once I think through all of these transformations, when we get to graphing, it's going to be so much easier. So what I'd like you to do is pause the video, and I'd like you to try example 3 and example 4 on your own. I want you to identify what transformations will happen, where is the vertex, and then if the table is going to be affected. That parent graph table, what will it then look like? All right, so for example 3, hopefully you were able to identify that the vertex will be at 1, negative 4. The transformations are that it's going to reflect over the x-axis. It's going to shift right 1 and down 4, so that's where I get my 1, negative 4. And then it's going to take the parent graph table of 1, 1, 2, 4, 3, 9, and instead of going over 1, up 1, it's reflecting over the x-axis. So now instead of going up, it's going to go down. So over 1, down 1, over 2, down 4, over 3, down 9. Because there's no reflector compressed, so the values stay the same. It's just that my movement is changing. I'm going down instead of up. And then for example 4, I have a compress of 1/2. I'm shifting left 2 and I'm shifting down 3. So if I shift left, that's a negative motion, and down is a negative motion. So my vertex is at negative 2, negative 3. And that compress of 1/2 took my over 1, up 1, over 2, up 4, over 3, up 9, and it divided those values in half because I'm taking half of it. So it's really going to be over 1, up 1/2, over 2, up 2, over 3, up 4.5. All right, so that is the bulk of what we're doing. We now just have to take that information and put it on a graph, which is pretty straightforward now that we've done the hard work. So I'd just like you to take a minute and pause the video and do an interaction because I've just thrown a lot of information at you. And what I really want you to interact on is mostly the this last slide that we were just on, where identifying the shifts and then also the stretch or compress of an equation. So what questions do you have? What examples do you want to talk through tomorrow in your CSG? What do you need to remember? What visual can help you? What is important information from what you just took notes on? And how are you feeling about it? All right, so what I've done here is these are the exact examples that we've just worked through. So this is example 1, the first one that I modeled. These were the transformations that we came up with because it's -3, so it shifts right 3 and add 4. So you'll be referencing the 4 examples that we just did. Now we're putting them on a graph. So over here I have just the parent graph. So 0, 0, over 1, up 1, over 2, up 4, over 3, up 9, and then reflect those same points. So in vertex form, this graph right here is going to take the parent graph and it's going to shift right 3 and up 4. Meaning that every point is going to shift right 3, up 4. So I'm going to start with the vertex, and it's going to shift right 3 and up 4. So this is now the vertex of my graph. So the point 1, 1 is going to shift over 3, up 4. The point 2, 4 is going to shift over 3, up 4. And it didn't have any vertical stretch or compress, so I don't necessarily have to take each one of those points and move them over. I can just apply the same pattern that the parent graph had. So from my vertex, I'm going to go over 1, up 1, over 2, up 4, over 3, up 9, and then reflect because this is my new vertex. And then 9 will be off the graph, and then I just reflect. So, pretend like that's a better line. There we go. So you can see that this transformation that occurred in vertex form just took my graph over 3, up 4, over 3, up 4, over 3, up 4, because it kept the same shape of the no vertical compress or stretch, and it just shifted everything over. So once I can analyze the equation in vertex form, it's a lot easier and faster than graphing in standard form. Alright, so this one had a shift left of 3 and a shift up of 1. So that tells me my vertex, which we had already identified previously, that my vertex is now at negative 3, negative 3, 1. And it has a vertical stretch of 2. So I just rewrote my table. Instead of going over 1, up 1, I'm going to go over 1, up 2 from my vertex. Because remember, everything is a movement from my vertex. And instead of going over 2, up 4, I'm going to go over 2, up 8. And then I'm going to reflect those points because I can't go over 8, up 18. Which I only need 5 points to make a graph. And I have them. So I can see that vertical stretch of 2. So I've applied all 3 transformations. It shifted left 3, up 1, and it had a vertical stretch of 2. So that is how I graph in vertex form. Alright, so I want you to pause the video, and I'd like you to try to graph this one on your own. Alright, hopefully you were able to at least graph that the vertex is at 1, negative 4, because it shifted right 1 and down 4. So from 0, 0, right 1, down 4. And then there was no stretch or compress, so we're still going to follow that 1, 1, 2, 4, 3, 9. But it's going to go down because this is reflecting over the x-axis. So instead of going up, I'm going to go over 1, down 1, and reflect, over 2, down 4, and reflect. And example 4, our final example of graphing from vertex form. I'd like you to try this one on your own. Alright, so on this one, hopefully you were able to put the vertex at negative 2, negative 3 because it shifts left 2 and down 3. And then it has that vertical compress of 1/2. So instead of going over 1, up 1 from the vertex, I'm going over 1, up 1/2. Instead of going over 2, up 4, I'm going over 2, up 2. Instead of going over 3, up 9, I'm going over 3, up 4.5. So I can see that that is getting wider, or it's being compressed down, because I'm only taking half of what the parent graph normally outputs. Alright, so go ahead and pause the video and have an interaction in your notes. What questions do you have? Which examples do you want to talk about? What are your understandings? What do you understand so that when you go to your CSG, you can just whip out, these are the things I understand because of this interaction. So we now know how to not only find the vertex, but graph it. Not only identify, stretch, or compress, but also be able to graph that and other points on the parabola. Okay, so the last thing we're going to do is, given a set of transformations, can I write the equation? So just a reminder, our general formula is y equals a times the quantity of x minus h squared plus k. So this is my stretch or compress and reflection. This is my horizontal shift, and this is my vertical shift. So I'm going to read the first example, and I'm going to see if I can put it in that generalized formula. So I see that I shift down 3, so that's going to be a vertical shift. Right 2 is going to be a horizontal shift, and I have stretch of 3. So stretch is A, right is a horizontal shift, so that's H, and down is K. So I just go over to my formula and I plug it in. So y equals stretch of 3 times x minus, if I'm going right 2, that's a positive movement, so I just put that in, squared, and down 3, minus 3. So that is those transformations in vertex form. Okay, so looking at number 2, I'm shifting left 1, and I'm reflecting. So left is an H movement, and reflecting is an A, impacts the A. So I'm going to go to my general formula, y equals, there's no stretch or compress, so there's no value going in for A other than 1, but it's just going to be negative. And then it's going to be x minus, and if I'm going left, it's going to be negative. So it's like x minus 1, which minus 1, just minus a negative, is really just plus 1 squared. And I don't have any vertical, so k is going to stay. It's like a 0 because I have 0 movement up or down. So that is that description in vertex form. So go ahead and pause the video, and I'd like you to try the remaining 3 examples on your own. Alright, so for this one, hopefully you were able to come up with y equals negative 1/3 x squared plus 5. Now you may have it look like this because inside the parentheses there is 0 movement right or left. Well, what's x minus 0? It's always just going to be x, so those parentheses serve no purpose. So when there's no left or right movement, those parentheses can go away. And so I had a compression of 1/3. I reflected, so negative, and I shifted up 5, so plus 5 on the end. All right, same is true down here. I don't need all that other stuff. If I'm just reflecting, then it just takes the parent graph and puts a negative in front of it. And then the last one, I shifted right 3, so my 3 is on the inside, and it's it's minus that value, and if that value is positive, then it's just going to stay minus 3, and a vertical compress of 1/2. Alright guys, so that is graphing the quadratic function in vertex form. Given a set of transformations, I can put it in an equation. So go ahead and pause the video and reflect on what we just did. Given those transformations, what are things you're going to need to remember? What was new learning for you? What questions do you have? And I'll see you tomorrow.